All right, sorry about that little delay. The goal today is to be really good at this one thing that's not actually that bad. So we're going to use the information from the lab we did yesterday to work through this idea. And this process, and I hope you did your reading because the upfront part, I'm kind of skipping a little. The process that we're going to go over today is this idea of net ionic equations. All right? This is a really important thing because the way you write your chemical equations from now on and on the AP test, you have to follow these rules because sometimes in chemistry, there's way less going on than you think there is. And that's actually kind of nice. The net ionic just shows the real chemistry and it ignores all the rest. So to do this, let's look at our lab yesterday. Now, I want you to, you're going to end up writing all of these chemical reactions. If you wrote them already, just start a new sheet so you can write them in this way. All right, so yesterday's lab, you added stuff together. The first one that formed a precipitate formed something that was grello, which is my word for greenish yellow, right? So what you're supposed to do from the instructions is all right, grello had a chemical formula, and its chemical formula was what from your instruction sheet? All right, it is AgI. All right, and then I'm going to put my arrow. Now, grello came when you mixed two bottles together. One bottle was letter what? A, and the other one is B. A plus B made grello. All right, from your instruction sheet, it told you that A was what chemical? Ki. So now let's use our brains. It's not super hard here, I hope. If you made AgI and I came with K, then B must at least have what in it? It must have Ag in it, correct? All right, so now you would look at your instruction sheet and you would look at the top things and you would notice that silver came to the party with someone else. Who'd they come with? They came with NO3. So it turns out when you take potassium iodide and you react it with AgNO3 or silver nitrate, you form silver iodide, but we're not done yet. Where did nitrate go? All right, it's over here somewhere. All right, and where'd the potassium go? Well, they're just hanging over there, doing their own thing. Okay, so this is the first reaction that we're going to write. I didn't do a very good job of my spacing here. Stick with me just for a second. That's actually here, the molecular. Oh, that's attached. Some of those heels. That was making me nervous. Thank you. Jan, Jacob, and Chase. You got to go to the office and pick up your ID cards that you never picked up. You're not one of them. Chase will leave a Jan. Jacob. Oh, I can see why. Sorry. Then Rachel. Yeah. Okay, so the way that this reaction is written, we call this the molecular equation. Make sure you know the three versions. All trimester or all year, whatever, all year long we have been doing the molecular equation when we've been writing our equations out. All right? But chapter 4 expects more. Oh, that's a good little limerick there. I like it. Chapter 4 expects more. All right? So we now have what we call the ionic. Okay, so let's just review real fast. What is an ion? All right, it's a charged particle. The ionic reaction will write this all out as charged particles. All right, so when we write the ionic equation, we write all of them as if, well, not as if, in their ion form. Because remember, these were in solutions, correct? And you read overnight or yesterday, whenever, that when you add certain things to solutions, they dissolve or dissociate into ions. All right, now, first I should balance this one. Let's not skip that part. There is no balancing here, right? But if it was not balanced, we would have to balance it. So it's just 1, 1, 1, 1. No, you have to do this only for the ones that produce colors, which I think is only 5. Is that right? All right, so here we go. It's not as much work in the long run as you think. So the ionic will be written as K plus. This is going to get ugly. Let me thin my marker point. So we have K plus I minus plus Ag plus NO3 minus goes to. Now, look, the thing that makes the color is called a precipitate. From your reading, hopefully you picked up the idea that a precipitate is when two soluble things react to form an insoluble product. All right, we'll show you these definitions here in a minute. But the precipitate in the ionic form is written together. It's not broken up anymore. That's why it was a different color. And then we have plus KNO3. Not KNO3. What am I doing? Slap me next time, Taylor. You're right there. K plus NO3 minus. Because this is the thing that created the precipitate. The precipitate is a precipitate because it is no longer soluble, or meaning it is no longer in ionic form. It's stuck. These two things are bonded. They are not soluble in water, and they will stick together forever. Everything else, though, it's just hanging out as an ion. You with me so far? All right, now, the net ionic equation is what really happens. Because look, there's a lot of stuff in chemistry that doesn't actually happen. And let's think about this high school. There's a lot of people that walk around in it and never find their soulmate, right? Like most of you. All right, so you're not actively like hanging out with anyone. You're just a spectator of all the weirdies that make out in the hall, right? Like you don't want to look, but for some reason you're like, okay, you go, girl. Can't say what I was about to say on video. All right, so now there's a new word, hopefully in your reading that you got it. The new word is a spectator ion. A spectator ion, first off, is an ion that is not part of the actual reaction. Because look, the only thing that really happened in this little micro well is we made that, right? So what did K and NO3 have to do with it? Nothing. Like they came to the party, but they did nothing. So we eliminate spectator ions when we write the net ionic equation. So then we would now write the only things that are left. We would put I minus plus Ag plus goes to AgI solid. I do not have anything left. First hour girl got them all. Mr. Colomore, I believe, has like 5 or 10 left. Way to not come to school until now. Oh, okay. I guess you're not a failure. Okay, are you all right with this? I hope that it's not bad, because if you think about it, the net ionic simplifies the heck out of it, doesn't it? It's the only thing that happened. All right? Now, I'll tell you an awkward story. When I was 22, be actually John and his friend, and then this was me and what's-her-face from Orem High School. Jailbait, I believe is what they call that right there, right? There was nothing there. All right? We've all been somewhere where your friends had a ton of fun and you probably didn't. You were just a spectator. In chemistry, there are things that are always just lonely spectator, like potassium, like nitrate. These two never get to do anything. From your reading, maybe you noticed the solubility rules. K and NO3 are hopelessly always alone. We're all right with that, right? Some people like to be alone. I don't know who they are, but I'm sure that they are. Just kidding. Whoa, don't yell at me.
If you add just K, no Ki, to Ag and silver nitrate, would it have a single replacement reaction?
That's a S there, not. Now this is aqueous. Is that what you're saying? Okay, this would be super complicated. You would end up with K plus NO3 minus plus Ag solid plus hydrogen gas. Because in solution, this is really surrounded by H2O. And when K reacts with that, it makes KOH plus H2 gas and heat and light, and it explodes. So this would actually be pretty fun to do. But it'd be pretty complicated. All right, here we go. I did this one. Let's have you practice. One of these made the color yellow, the really bright yellow, right? Yeah. What letters combine to make yellow? A and C. Okay. Give me the molecular, give me the ionic, and give me the net ionic. Little follow-up story on my friend John. I got engaged and I called him to tell him, and he answered the phone, and he's like, he just picks it up and he's like, Dave, well, he said Tom, sorry. Tom, I'm getting married. We got engaged on the same day. He's like, all right, that's cool. Well, me too. But anyway, there, bye-bye. He did not marry someone 5 years younger than him. But I did. Yeah, I was 25, so it was not as sketchy as it sounded. Yeah, if you didn't have to write it down. Anyone need this instruction sheet to help them out? You need it? You got it? I'm going to have to edit this recording a lot. So let's go ahead and write this one through. This one has just a maybe a wrinkle or two that will help us actually to do these even better. So first off, the formula of A is still the same. It was Ki before, it'll still be Ki now. Letter C, that was Pb. Am I on acetate now? Okay, last hour I wrote NO3 like 3 times on accident. Stop me if I do. And that produces PbI2, that's your yellow stuff, right? So we're going to say that's my precipitate, or my solid, plus the other 2 parts left over are KC2H3O2. Then, the last one I didn't have to balance. The last one, every charge of everything was 1, so that means all your coefficients will be 1. This one, it is not. So if I have 2 I's, bless you, I have to put a 2 there. 2 K's means I've put a 2 there. That makes 2 acetates, but I have 2 acetates, so 1 and 1. Now, the coefficients and subscripts have to be represented when we write the ionic overall. So make sure that this makes sense to you. I'm going to start over here, but you will have 2K plus, oh, I made it thin, I swear, plus 2I minus, plus Pb plus 2, and then take a time out and look up here so you make sure it makes sense. This subscript right here, that means there's how many acetates? There's 2, so you have to put the 2 out here. That produces, this is together. How come it's together? Because it's my solid or my precipitate. What'd I do wrong, John?
I'm written.
Oh, I thought, sorry.
Well, I just put the parentheses and then 2 to the right in the subscript.
No, can't do that. That would mean they're attached to each other. And they're not. They're 2 independent things. All right. So let's make sure that this makes sense because it can be very tricky. Look right here. This 2, just like Brennan was saying, he put the 2 right here in parentheses. That's tempting because it is there, but a subscript will tie things together, just like these things have to stay there because that ties the whole acetate thing together. But this 2 just means there's 2 of them, so it goes here. Now, I know this is confusing. This 2 in this means that there's 2 of them connected to 1 Pb. But really, if they're aqueous, then they're broken apart. Okay, now, time to get rid of my spectators. Potassium, wah, wah, wah. It never gets to hang out with anybody. All right, then my acetate, same thing. So what's the only real thing that really happened here? 2 iodides found their BFF.
How do you know which one to cross out?
All right, there's a couple of things. They're not in the precipitate, or, and it's important that it's an or, not either. It's or, they're exactly the same on both sides of the arrow. It's a K plus, it's a K plus. Notice here it's a Pb plus 2, but over here it's a Pb stuck to an I. They have to be exactly the same on both sides of the arrow and able to cross them out. So this is the Net Ionic Equation. This is the only real chemistry that happened in that. And it's the chemistry that made your 2 clear things create something that was yellow. This yellow thing is called lead 2 iodide, and it is the precipitate. Now, you were supposed to pick these words up in the reading, but in case you have not, here's some vocab words. Ion is a charged particles. Cations are positive, anions are negative. Ions form ionic compounds, which are compounds made out of ions. Ionic compounds are generally good at breaking apart in water, or what we call dissociating. All right? Solubility is whether or not something dissolves. I had an A in there, that's why it looks weird. All right? So ionic things generally have fairly high solubilities, but not all of them. In fact, let's think real quick. I'll come back, don't worry. In this example, 3 of these compounds had high solubility and 1 had no solubility. Which one had no solubility? The PBI2, my precipitate, right? That's its definition. It is the one that will not dissociate or dissolve or break apart, whatever you want to say. Then, here we have a precipitate. It's an insoluble product formed in a chemical reaction. There's a much more complicated definition for it, but this is good enough for right now. It's the one at the end that we put in parentheses and put an S. S means solid. The other ones would have a parentheses and an AQ. AQ means they are in solution or dissolved. Next, an electrolyte. This is tricky. Like sugar dissolves, but sugar is not an electrolyte. In this chapter, we're worried mostly about electrolytes. An electrolyte is substances that dissolve or really dissociates in water. And what that means, this picture's trying to show you, ignore this arrow for right now. It means that a chunk of salt, when placed in water, it does dissolve, meaning it breaks into small parts, but it goes a step farther. 1 second. The actual Na and the actual Cl's will separate from each other. They disassociate. So now, instead of NaCl in water, you have Na plus and Cl minus in water. Or you have ions. 2 seconds. Ions let electricity flow through your solution, so we call it an electrolyte. Okay, yes?
So he has to make electricity close to it.
To be considered an electrolyte, it has to let electricity flow through water.
Does it have to be ionic to do it? Or
It has to have charges, so it has to be ionic. Because if you take just pure water, like not tap water is too dirty. But if you take distilled water and you add sugar to it, and you put electricity in, nothing will happen. There's no flow of current from here to there, because in order to have current flow, you have to have plus and minus charges, which come from, right here, ionic compounds. Okay, I think that's all the definitions I had. Okay, let's come back here then. We can talk through these things. This would be considered a strong electrolyte. It dissociates 100% when placed in water. Well, nothing dissociates 100%, but very close to it. Lead to acetate, a strong electrolyte. Lead to iodide is a non-electrolyte. And, you know, it's probably actually considered a very, very weak electrolyte, but for our purposes right now, it's a non-electrolyte. And this would be considered a strong. This one is like mega, mega strong electrolyte. All right? So those 3 are electrolytes, or they are soluble. The precipitate is considered insoluble. All right, now I'm going to erase all this. Let's keep going. We've done 3 of them, right? There's 2 more. What made brown? So B and D, right? Okay, do this as quickly as you can. Molecular, ionic, net ionic. These should become very quick. Maybe not yet, but they should eventually. All right. B, was this lead acetate? Oh man, that one sucks to write. But I got this. Oh, B is not lead acetate? Oh yeah, C is sweet, because I didn't want to write that anyway. AgNO3 plus NaOH, right? Went to brown was the AgOH, correct? Plus what two things were left over? NO3. Hey, if you look at the periodic table, do you notice that K is right below Na?
Yeah.
All right, and what would be above Na? Lithium. What's below K? Oh, I have dyslexia sometimes. All right, all of these are family 1 metals, and they are never part of the precipitate. Or another way to say it, family 1 metals are always considered something. Oh, gosh. Spectator ions. I thought that one was easier. No, not prospector, Bill. Whatever his name was. All right, here we go. So the ionic, remember, all of these will be written apart. And everything was a plus or minus 1, so there's no balancing needed. Ag plus NO3 minus plus Na plus OH minus goes to, this was my solid, right? AgOH solid plus Na plus NO3 minus. Whew, that was fun. NO3 is always a spectator, right? Go ahead, Tucker. What? By memorizing a bunch of rules that you're going to memorize over the next 72 hours. Yeah. Yeah, like if sodium was a 2, you'd put a 2 here. Yep. Right. All right, then those are my spectators. So what really happened in this beaker? Ag found OH minus, and they stuck together to make AgOH solid. That's what happened. Okay, let's think about this. NO3, always a what? Spectator. Na, always a spectator. But look right here. Silver's confusing because when it's with NO3, it's out hanging by itself. When it's with OH, though, it's stuck. So silver doesn't have an always rule. Whether silver forms a precipitate or not depends on who it's hanging out with. All right? And that's part of my solubility rules in your book and in a sweet 9-minute long video that you should watch. It will help you with solubility rules. All right? We've already learned some. Oh, hey, Siri, what's up? On Monday, a girl in driver's ed, her phone was sitting in the little pocket, and it said, "What can I help you with, baby Beyonce?" Like, oh, hey. So I saw her this morning. Like, what up, baby Beyonce? She's like, oh my. I'm like, oh, whatever. So somewhere in our speech, we must have said something that sounded like Siri or something. I don't know how it worked, but it was funny. All right. Now, so back to focusing here. These rules, whether something dissociates or associates, they need to be understood. You need to read them, but we'll practice. We already know some. We now know that family 1, always a precipitate. NO3, always a precipitate. I erased it. Acetate, sorry, spectators, thank you. Always spectators. C2H3O2 minus, always a spectator ion. We all right with that? Okay, we have one of these left to do. We made gold. No, we didn't really. Yes, we are true alchemists now. All right.
What about the red?
Oh, did I skip the orange one? Okay, we can do that too. Sorry. Okay, we made gold, but what made gold? All right. F plus D made gold. Plus something else. I'm pretty sure you're right. E's the one you had to just use by elimination, right? Okay, so there's your Net Ionic Equation for the production of our mercury 2 hydroxide. Now for the orange, just give me the Net Ionic. Okay, so these go fast because as long as you know the formula of the precipitate, it's super easy. It was what? Hg, not Ag, sorry. Hg, right? And what was it hanging out with? So what must have made this? That is all you have to do. If all you're asked for is the Net Ionic, find the thing that is the precipitate, put it on the right side, and then make it on the left side. Like find the parts that are required.
Do you even really have to know which ones are spectators? Because don't you just look at the ending and then do what adds up to it?
Well, sure, you don't need to care, except for test problems. We'll always say, what are the spectator ions? Because I'm a butt face. But this scale of 1 to 10 of what we've learned in this class, this isn't that hard, right? Okay? What I need you to do tonight, I want you to look at the solubility chart. You don't have to memorize it anymore. You used to have that memorized until 3 years ago. They changed the AP test. But you do need to know how to use it, apply it, and to do that, there's a little video that you can watch. It's not me. It's from the internet. It's probably on Guru and the other ones. I can't remember if it's on both. Look on the main page first, and if it's not there, go to Guru. But anyway, watch the video for solubility rules and come back tomorrow ready. Now, the homework is due tomorrow. It's the blue sheet that you write the answers for, and then you submit the homework on a form. It shouldn't be that hard. You got to move your hand out of your mouth. Say that again now. Look, you can always turn your homework in late, and that's probably bad teaching right there. The advantage to turning your homework in on time is that that's when I will stop talking about it, if that makes sense. So when you're late, what you're trying to do is make up work while you're trying to learn new, and then it gets hard. So yeah, you can still turn it in on Monday. That's not that big a deal. Both, yes. The blue sheet you were supposed to do, you're welcome, Julie. It's because I love you. All right? You're supposed to do is you read section 4.1 and 4.2. Has anyone in this class done the blue sheet? Did it take, how long did it take?
2 hours.
No, it did not take 2 hours. That was the worst answer ever. Get out of my room.